So today we're going to go over chapter 10. We're only going to cover a little bit of chapter 10. We won't be able to finish all of it. So we're going to probably do about a good 30 or 40-minute video today. And then after that, we will do another 30 to 40-minute video on the end of chapter 10. And then we'll be done with the course from what I really want to cover. So it says, in this chapter, we will look at a relationship or a correlation between two variables. We will construct an equation to describe the relationship and use this equation to predict one variable value from the value of the other variable. We will primarily be looking at the relationship between two quantitative numerical variables. Okay, so I think in your homework, this will be called 10.1. For our notes, it'll be called 10.2. So it says in part 1, the basic concept of correlation. When looking at the relationship between two variables, oftentimes one variable helps explain the other. So if you guys come down here, a correlation exists between two variables when the values of one variable are associated with the values of the other. So this is something we're kind of used to doing. A linear correlation exists between two variables when there is a correlation and the plotted points of the paired results pattern can be approximated by a straight line. So we're going to get into that. That'll be the line of best fit or the regression line. A response variable measures the outcome, and an explanatory variable may explain or influence changes in the response variable. So just for intro purposes, real quick, let's talk a little bit about response variables and explanatory variables. So beer and blood alcohol content levels. So how does drinking beer affect the level of alcohol in our blood? The legal limit for driving in most states is a blood alcohol content of 0.08%. Volunteers at Ohio State University drank different numbers of cans of beer. 30 minutes later, a police officer measured their blood alcohol content. What is the explanatory variable? So this will be our X in general, and then our response variable will be our Y, okay? So in this problem, the explanatory variable may explain or influence changes in the response. So the response is the percent in your blood alcohol content, okay? And what changes that is the number of beers you drank. So number of beers, okay? And the blood alcohol content level is based on the number of beers you drank. So that's our response variable, okay? So a sociologist looks at National Student Loan Survey data and is interested in looking at the amount of debt and income to explain stress caused by college debt. So what is the explanatory variable? Debt and income. Oops. So once again, this will be our X. And what is the response variable? Stress levels. Or your stress level or whatever, okay? So something that we're going to talk about. So a scatter plot may show a correlation or a non-linear, or may show a linear correlation or a non-linear correlation between two quantitative variables. We are looking for linear relationships between our two variables. Okay, so there is such a thing as a correlation, and then a specific type for our class will be a linear correlation. Okay, it says if you can identify an explanatory variable response or put the explanatory variable as the X and the response variable as the Y in general. If you can't, then you just do the best you can. So it says Leonardo da Vinci used measurements of bones and body parts to predict height and body types of a person. He represented his findings in his famous drawing, The Proportions of the Human Figure. I'm pretty sure that's the one you can, look up, and it's got the guy with his arms spread out. So below is a graph of a random sample of 55 adults, male and female, okay? So if you look right here, we got the left arm and we have our height, okay? So your height determines the length of your left arm. So, or you could do it the other way. You could measure your left arm and use that to determine your height. That's why they say it kind of doesn't matter which one you say if it's hard to tell. If one definitely affects the other, in a certain order, then it might matter, but in general, it shouldn't change too much of your relationship. So it says each point on the scatter plot represents an individual's measure on both variables. does there appear to be a linear relationship? So if I wanted to, I could draw like a line right through there, right? And that would seem to be a decent line that kind of averages out all the points. But again, it's kind of subjective. That's a little bit of the problem with this, is how good of a linear relationship is that? Well, I feel like it's a little bit linear, but maybe not perfect, or definitely not perfect, but maybe not even like super strong. But I do see that there could be some linear relationship there between arm length and height, or height and arm length, okay? In oil production, now if you look at this, this does not look linear in any way, right? You know, I want to try to draw a line through this, and that's just not going to work out. Now the problem is that we're going to use technology in this section, and the calculator will still try to find you a linear regression line, but you're not really supposed to try to use regression lines on things that do not have linear form of some kind. So this would definitely not be something that we want to think of as a linear relationship. So there is a relationship, but it is definitely not linear. So there are sometimes, or there are correlations that don't have to be linear correlations. Sometimes they're just correlations. Okay, so this is just kind of some background. So we have, if positive changes in X are associated with positive changes in Y, the direction of the association is positive. Okay, oops. If positive changes in X are associated with negative changes in Y's, the association is negative. Sometimes they'll say increasing in another class, or decreasing. Okay, or oftentimes it'll be referred to as a negative or positive association. Instead of just writing the letter, they might write out, or the plus or minus, they might write out positive versus negative association. So in this problem here, you see that we have the X's are going in the positive directions, as are the Y's. And so this gives us a positive association. The X's are still going in the positive direction, but now the Y's are not. That means we have a negative association, okay? Now this is what we were kind of talking about earlier. Do the points follow a single stream that is tight to the line, or is there considerable spread or variability around the line? So this one looks like a very strong linear relationship, right? Now this one, you might also be able to draw a linear relationship through there, but it looks a little bit weaker, okay? And there's such a thing as a linear relationship and a nonlinear. This could also be called a quadratic or parabolic relationship. So we're not going to get too much into this one. We won't really cover too much of that. We're going to focus much more on linear trends and linear relationships, okay? Or things that are close to linear. So there's a guideline. It's not really like an exact set of rules, but I'll go ahead and give it to you. I've looked it up in different books. I've also looked it up online. There's not a like exact number. It doesn't seem, different people have different views on it. So this is our strength of our relationship. And we're gonna say, we're gonna deal with something called the Pearson coefficient, R. And if R, the absolute value of R, is between 0 and 0.3, we're gonna call this a weak linear relationship. If the absolute value of R is between this and 0.7, we're gonna call this a moderate. Linear relationship. And then we're gonna have 0.8. We're gonna call this a strong linear relationship. Now here's the thing, you guys might notice there's a little bit of leeway in here. We have between 0.3 and 0.4, we're missing, you know, 0.35, 0.36. So that's why there's that gray area. I would, if I were you guys, I would definitely try to round to the closer one. So if you're like at 0.32, I would say that that's closer to a weak relationship. If you're at 0.39, I would say that's closer to a moderate, or you could even say a moderate weak, you know, or a weak moderate, you know. Again, it's not exact because I've actually seen different numberings from different books. So just kind of use this as your guideline. Okay. So measuring the strength of a linear, because the conclusions about relationships between two variables based on visual examination of scatter plots are largely subjective, we need a more precise objective way to explore relationships between variables. That's where this guy comes in, the linear correlation coefficient. So we're going to use this correlation coefficient R to help us decide if it's a weak, strong, or moderate relationship. So requirements: the sample of paired data is a random sample of independent quantitative data. Visual examination of the scatter plot must confirm that the points approximate a straight line pattern. So if you did this problem here, you would, or let's say we added some more to make it even more obvious, it's definitely not a linear trend, right? Or if we went up here to this problem, this is definitely not a linear trend. However, the technology we're going to use on our calculator to work with this will still tell us it has an R value, and it will still tell us it has a regression line. The problem is you should not even be using it for something like this. So don't, that's what they mean by visual inspection. You should only be using this if something you look at appears to have some kind of straight line. Again, that's still subjective as well, okay? Any outliers must be removed if they are known to be errors. The effects of any other outliers not due to error should be considered in the calculating of R without the outliers included. With and without the outliers included. So if there's an error and that causes the outlier, then you exclude it. But if there's an outlier, but it's not because of an error, then you have to keep it, okay? So here's the formula for calculating R. Looks rough, right? This is pretty rough, so we're not gonna worry about that. We're gonna do every calculation of R on our calculator, okay? So properties of linear correlations, the value of R is always between -1 and 1. So R will always be a value between -1 and 1. You don't have to worry about getting something other than that. The value of R does not change if all the values of either variable are converted to different units of the scale or a different scale. As long as everything is changed, then the R will still change or will still stay the same, whether you do it, you know, whatever the measurements change to. The relationship will stay the same. The value of R is not affected by choice of assigning the variables to independent and which variables to be dependent. Basically explanatory versus response. That's what they were talking about. Whether you choose the X or Y axis for one or the other should not change the value of R. R measures the strength and direction of a linear relationship, but is not designed to measure a relationship that is not linear. That's why they say with through inspection, you're supposed to kind of double check to see if you're even supposed to be using it, okay? Here it says, we wish to test whether an underlying correlation between two variables in the population. The correlation in the population is P. And this is what I was telling you guys about how they use another version of P. So this is not the P value. This is not population parameter for proportion. This is another letter P. It's kind of a cursive P. And it is, this is what we'll use for hypothesis test, okay? So basically we have two kind of ways that we can do this. We can do a full-blown hypothesis test, or we can kind of make sure that R is applicable, and then we can use R and compare it directly to a critical value, okay? So kind of skipping the hypothesis test and just jumping to steps 4 and 5 from what I taught you. Method 1, the correlation coefficient table, okay? So this is the first way you can do it. So interpreting R using the table, I'll show you that in just a second. And then you can put this into your calculator. Okay, I actually use this one down here all the time. I never use the one that I just circled above. So these are two different methods on your calculator. But I really prefer the linear regression T-test method versus linear regression A plus BX, okay? I'm just gonna be honest with you. I don't normally use this one. I primarily use this all the time, linear regression T-test. I don't really see a reason you would ever want to use the other one versus the below one, but they're both on there. Maybe there's some reason I just haven't encountered it yet. Okay. So we're going to use our calculator to do this, and I have downloaded the calculator app onto my computer, so I'm going to try to go through the steps with you on the calculator first, okay? So here it says compare, once you've entered it in your calculator, compare the absolute value of R from the calculator to the from the calculator output to the critical value in the table. If the absolute value of R from your data exceeds the critical value in the table, there is a significant linear correlation. If the absolute value of R from your data is below the critical value, there is not a significant linear correlation. Okay, so what we're going to do is we're going to look at this problem and we'll kind of go through it. So remember, this is method 1 using the calculator approach for both methods 1 or 2. I'm going to use linear regression t-test. So it says the following table displays the duration of an eruption of Old Faithful geyser and the time interval after eruption until the next eruption from a random sample. So basically they're trying to see if there's a relationship between how long until it erupts again versus how long it erupted for, okay? I'm assuming this is in minutes. They don't really say. Yeah, I'm going to assume this is in minutes because duration, oh, I guess. Well, they don't say. So I'm assuming the duration has to be in seconds because I can't imagine that it's erupting for 240 minutes straight. I've never been to Old Faithful, so I don't know how long it actually erupts, but I'm assuming it's not for 240 minutes. So I'm going to say the duration is in seconds and the interval after is probably in minutes or maybe hours. But for us, it's not really important, whatever the measurements are, because we're just trying to find the correlation between them. Is there a linear correlation or not? So what we're going to do is we're going to take out our calculator, okay, and let's go into stat, okay, and let's go into edit, and let's build list 1. So let's do 240, enter, 120, enter, 178, enter, 234, oops, 234, enter, 235, enter. Sorry guys, I didn't think to enter this in first. I should have. 255, enter, 220, enter. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. So that's good. Now let's go over to list 2. List 2 is going to be 92, 65, 72, 94 and 83, 94, 83, 94, 101, and 87. Okay, so double check all your stuff and make sure we're all on the same page. Now I'm going to quit and get out of here. Okay, so now I have this entered in. Okay, so on my calculator, I'm going to go into stat test linear regression t-test. So I'm going to go into, so let's go to graph. First, let me show you something really quick, you guys. So before we go straight into it, remember, we're not supposed to use linear regression or any of this unless there appears to be some kind of relationship. So I'm going to have to go into second function and then stat plot right here. Okay, so hopefully look on your screen where that red Y is. And I'm going to turn on my stat plot. Okay, so hit enter and I'm going to go to on. Okay, so now it's on. So then I'm going to quit and I'm going to graph. Okay, so I don't see anything. So then what I'm going to do is I'm going to go into stat. Oh, I'm sorry, not stat. Let's go to graph again. And I'm going to go into zoom. I'm going to go down to zoom stat until I find it. Should be one more. Zoom stat right there. So hit enter on zoom stat. And there you go. So if we were to draw a line, oops, if we were to draw a line, that kind of looks like a linear relationship to me. Maybe not perfect, but it definitely has some kind of linear relationship. So this is how we say, okay, linear regression t-test is going to work. So let me get out of here. And now I'm going to go into stat, tests, and I'm going to go to Linear Regression T-Test. Normally it's way here at the bottom, so I went all the way down to F, and I'm going to hit enter. And they want list 1 to be your X and list 2 to be your Y. You say sure. Okay. In general, I use not equal to. Most of the problems we're going to deal with are going to be not equal. And let's see what we got here. So I get an R value. Oops. I think I might have entered. Oops, hold on. There we go. Okay. So I thought I entered in a value wrong because I wasn't getting the right number. So you have to scroll down a little bit to get your R. So you see the very bottom value, R equals 0.925. I'm going to call it 0.926. Okay. And there's also an R squared. By the way, do you notice there's also a T value and a P value? So that means we're also going to be doing hypothesis tests with very similar features. So lots of information on the screen, but what we're concerned about is this R value of 0.926. So I'm going to go back to here. Okay, so we said stat. So we did, let me see here, test. So we did Lin Regression T-Test, and that gave us R equals 0.926. Okay, now if we use our little table, over here, that tells me that my R, and I shouldn't say my table, if I use my little guidelines, that tells me that this is a strong linear relationship, okay? So technically, I have a feeling this is a strong linear relationship, but I'm going to use the correlation with a significance level of 0.05. So this is my R value, okay? And now we're going to use the critical value method to test it, okay? So now I have to go to my table, and this, you guys should all have this printed out at this point. So I have it right here, and it is, I forget which page this is. This is like the 3rd or 4th page, I'm not sure. But right here it says critical values of the Pearson correlation coefficient R, okay? So notice they have very specific alphas. These are the 2 alphas they list for us, so that's pretty much all we work with is alpha equals 0.05 and alpha equals 0.01, okay? So in this particular problem, there were 8 pairs, right? There were 8 pairs. So I'm here, and then what was my significance level? They say 0.05, so that's here. So this is my number. So I have 0.707 as my critical value. So I'm going to come back over here, and I'm going to go to 0.707. So crit value equals 0.707. So now we compare our R to the critical value. And if our R is bigger than the critical value, okay, so 0.926 is greater than 0.707. So this is crit value. And this is our R value, okay? So if our critical value is greater than our R value, there is a linear correlation, okay? So whenever your R value exceeds your critical value, you have a linear correlation, okay? So that's kind of the fast way to do it. And in this case, we know it's not just any linear correlation, it is a strong correlation. So we have a significant linear correlation between the duration of Old Faithful and the interval after how long until it erupts again, okay? So this is how you can use that R value. Very quick, very clean, all right? Here's another problem, but this one I would like to do a hypothesis test on like we've been doing, okay? So it says coffee is a leading export from several developing countries. When coffee prices are high, farmers farmers, you guys know that's farmers, often clear forests to plant more coffee trees. Here are 5 random years data on prices paid to grow coffee and the percent of forest loss in a national park that lies in a coffee producing region. So basically, as the price of coffee goes up, people clear more land because they want to make more coffee, and they want to see if this is a linear correlation. Again, that's specific. What we're looking for is a linear correlation. Okay. So in the past, I've actually asked a question on my exam very similar to this one. So make sure you know how to do this. I have to search through the online test bank to make sure they have something similar, but this is a really good test question. This one is also a really good test question, but it's a quick test question because you're not really doing a full-on hypothesis test. You're just comparing your critical value to your R value, okay? So state the null and alternative hypothesis. So we know step 1, this cursive P, this will be our claim. And again, you almost lose, for these particular ones, feels like you lose the claim and opposite because we're always going to be doing it the same way. So the claim is always that this cursive P for our class will not be equal to 0, and then P equals 0. So then step 2 will be the null and the alternate, which again, for our class, the null will always be P equals 0 and P not equals to 0. I'm not going to go into the less than or greater than for these type of problems. So if you look up here, these are your options, but I'm going to try to stick to the not equal to, okay? And then we have step 3, our standard alpha equals, what do they say, 0.05. Okay, so this is a two-tailed test. Okay, so we're going to compute the test statistic. So the first thing we have to do is we have to go to our calculator. Okay, and let's enter this into our calculator. So let's go into stat, edit, and we have to change our lists. Okay, so let's see here. We got 29, 40 and 54, 40, 54, 55, and 72. Oops. So we should have 1, 2, 3, 4, 5 values. Yep. Okay, so let's go over here. We have 0.49. We have 1.59. We have 1.69. We have 1.82. And we have 3.10. Okay, so now we're going to go into y equals, graph. Now, once again, it doesn't show us what we want, so we're going to go into zoom, and we're going to go down until we find zoom stat. So we get something like this. So does that look like a linear relationship? Looks like we could draw a little bit of a line right through there. Okay, so now I'm going to quit. Okay, now I'm going to go back into stat. I'm going to go to test, and I'm going to go linear regression T-test like we did last time. Let's hit enter. Okay, so we're going to use list 1, list 2. Everything's the same, it looks like. Okay, so this time we're going to use this T value and this P value. Okay, now it still gives us R, 0.95. So I'm really sure that this is going to be a linear relationship, but I'm going to do the hypothesis test method this time. So my T is 5.59, I guess, and then our P will be 0.0113. Okay, I'll use T equals, so we're going to do step 4. So we did test Lin Regression T-Test, and that gave us T equals 5.587. I think I said I was going to do 5.59, but in my notes I have 5.587, so let's just use that. And then my P value equals this p-value equals 0.0113. Okay. Now statistical decision. We're going to do just like our normal test statistic stuff and hypothesis testing. Well, we know that our p-value is 0.0013. We know that our alpha level is 0.05. So we're going to say since 0.0113 is less than 0.05, which equals alpha, we reject the null and accept or support the alternate hypothesis. So I want to remind you guys of something. I don't think I wrote it for you up here, so let's go back up here. So this means no linear correlation or no significant linear correlation, and this means linear correlation. Okay, so keep that in mind. The null is saying that there is not a linear correlation, and the alternate is saying there is a correlation, whether it's positive or negative or whatever. We can go from there. Okay, so I'm going to come here and we're accepting the alternate, and the alternate says is a linear correlation. So we're going to accept that. So he says there is sufficient evidence to support the claim that there is a linear correlation between prices of coffee and what was it saying? Forest area lost and percent of forest area lost. Okay, so that's how you kind of can do the beginning of chapter 10. I'm going to end it there so you can get started on some of the homework using the R value, the Pearson coefficient. This is our often referred to as the Pearson coefficient. Okay, and you can use that, or we can just go full-blown hypothesis test with the p-value. And we can get both of those or all of the information we need from linear regression t-test. Okay, so that's a very important one. So if somebody asks you to find a linear correlation, this is how you do it with hypothesis test, and this is how you compare critical values to your R. Okay, and again, you're only supposed to be using this if there already is some visual, through visual inspection, a linear correlation. Okay, because even if you do a problem that's not linear with a linear correlation, it'll still give you values. The calculator will still try its best to give you a regression line and everything like that. So we're gonna kind of, let me see, I don't know how much I wanna do on this. I guess I could, let's see how much we have left in the next video. I better go another one. That looks like a lot of pages left. Some of it's pretty quick though. Not all of it takes a long time. Okay, so let me look at this last one here. So it says, the square of the correlation, R squared, is the proportion of variation in the values of Y that are explained by the least squares regression of Y on X. We recall that R squared, the coefficient of determination, or we call the R squared the coefficient of determination. The value of R squared tells us the percent of variance of one variable Y that is predictable from the other variable X. It gives a proportion of percent of variation in Y that can be explained by X. So we could use the supermodel problem listed below. I think we're going to later on do one with miles per gallon of a car and weight of cars. So you're going to notice that it seems like the heavier the car is, the worse its miles per gallon is. So we're going to try to come up with how much of the variance in the variation in miles per gallon can be explained by the change in weight of cars. So, you know, like comparing a big giant truck, like a big Ford F-150 or a Toyota Tundra to a smaller, lighter, you know, Honda Civic or something like that, or, you know, a Chevy Cruze or something. Why do those cars get better fuel economy? Well, there's multiple reasons, but one of the biggest reasons is weight, and we want to know why do trucks, or why do or how much does weight affect the variance or variation in miles per gallon. So in this problem, it says listed below are the heights and weights of 9 randomly selected supermodels. Calculate the correlation coefficient, and then what percent of variation in weight can be accounted for by height. So let's just finish this last piece right here. So let's take out our calculator. Okay. And by the way, you guys should all have this calculator if you need it on your computer as well. I think they're giving out like a 90 or 6-month free trial, so maybe you can use it in the summer as well if you're struggling for a calculator. I should have sent you the link out. You may have missed it, but there was a link from earlier in the semester. Hold on, you guys. There's an airplane real quick, or a helicopter. Okay, so let's write, let's do this. Okay, so let's plug in these values. So let's go into stat, edit, and let's plug these in. So 71, 70.5, 71, 72, 70, 70, 66.5, 70, and 71. And that was 9. Okay, good. So now let's do these 125, 119, 128, 128, 119, 127, 105, 123, 115. Okay, so hopefully I entered it all in right. So now we can quit, we can get out of here. Now we can go into stat test, and we're going to go to Linear Regression T-Test, right? So I'm going to hit enter, and we're going to do just like before. We're going to calculate, and then we're going to scroll down to our R and our R squared. Okay, so it says that R is 0.7955, so we could do 0.796, and it says R squared is 0.633-ish, give or take. So let's do that. So let's plug those into our values here. So R, so Linear Regression T-Test, and that gave us R equals 0.796. Okay, so we're feeling like this is a pretty strong relationship. One thing I forgot to do, let me go back. I made a mistake. What am I supposed to do first? I'm supposed to go into stat. Oops, it's graph. But notice again, I'm going into graph and it doesn't show up. So I go into zoom and I got to go to stat. Okay, there's zoom stat right there. Let's hit enter. So there it is. That kind of feels like if I drew a line. So up here, there appears on the top right of my screen, there appears to be some kind of a line there. But I'm not super sold on that. But if I'm being kind of honest, if it weren't for the bottom one, I feel like it's a linear relationship of some kind. If I drew a line through the middle, I feel like it kind of would average it out and I'd get a nice little regression line. So it does appear to be some kind of linear relationship. Again, it has to be really ridiculously off to not be a linear relationship. So we're going to come over here and we're going to see, oops, I did it again. So now we're going to say that there is our R is equal to 0.796. And then it says that R squared is equal to 0.633, which is about 63.3% of the variation of weight is explained by height. So what this is saying is that there is a variation in weights, but 63% of that variation in weight can be explained by the variation in heights, okay, by the different heights. So that's what the R squared means. Again, these are things that if you guys go much further in statistics, you'll use a lot more than I ever have. This is kind of, I guess, some of the last info that I did on these types. When you get into higher levels of calculus and you get into higher levels, upper division statistics, you start doing a bunch of different probability with integration and things like that. So in my experience, I haven't used this too much, but you guys, if you go on to be statisticians, you may use this much more than I have, okay? And again, the pages might be off a little bit because I think there was some kind of shift in the PDF. So you guys might have this carrying over into the next page. Don't stress about it, just kind of follow along best you can. So I'm gonna go ahead and stop right there for this video, and I will end chapter 10 in the next video, and we should be done with the course.